So we're going to get started now. We are the lightning detection and warning system. My name is Claude.
My name is Charles.
We have a third member, Brian, but he's out of the country right now, so he wasn't able to make it to this. So we're going to start with a project description.
So our project is to design and construct a lightning detection system. This will have two channels of verification. One is a RF antenna, and the other is a flash detection system. And we are going to try to have this be able to upload information to a web server for viewing.
So here's our basic system block diagram. So here we have our two input signals, so the RF signal and the short bursts of light. Through the RF signal will be detected by an antenna, which we'll get more into the design of that later. And then that signal will be passed from the antenna to a conditioning circuit to be transmitted from an analog to digital signal. And then that will be inputted into a microcontroller's ADC, which will then use it. And then we'll use the microcontroller to wirelessly transmit the data to a web server. And then the other side of the channel will be a light detection system using photodiodes. And that will also pass a digital 0 or 1 to the microcontroller. And then that will also transmit the information to our website. And we'll go a little bit more into the details of how the microcontroller handles that set of information.
Okay, so the block diagram for our Arduino is pretty simple. We have basically two inputs. One is the ADC for the RF detection. The other is a ADC for our light detection system, which when we get a signal from both, we know we are confirming that we have seen a flash and a transmission from the strike of lightning. And that would go upload data to the website with a timestamp of when it happened. Basically.
Yeah, so if the RF gets a good signal, so it receives a frequency within our range, it will send that to basically an AND gate, and then it will take as well as the 0, 1 from the Arduino and compare the two. If they're both high, it will output lightning detection to the website, and if only one is high, we have a situation set up for that. So we'll move on to that in a bit. So
for the RF signal, what range are you listening?
We are looking at specifically 300 kilohertz. Based off of the fact that it's a 1 kilometer wavelength, and that made a lot of the mathematics a bit easier to use. Yeah. Here's our Arduino setup for just testing the board as of right now.
So right now we are using a Adafruit feather board for our Arduino. We have our GPS unit that will give us an accurate location and time. We're mostly concerned about the time stamp with this. If we were to expand this to multiple detectors, we could then use the GPS locations to triangulate where lightning strikes. We also have an LCD display that will display messages as like the status of the device, and there's also the LED indicators, which also tell you what the status is further away. This specific board we chose because it does have built-in Wi-Fi capabilities, so we can just connect that to the internet really easily.
Where's the ATC? Yeah, where's the detection?
So right now the detection aren't hooked up to this. But they're these ports.
It's P01 and P04 on the left side rail.
So sample of what would be shown on the LCD, and this LCD is an I2C communication with the Arduino, so we only have 4 cables instead of 16. And it is a 16x2 LCD board. We have our website, which I've been continuing to keep updated. If you want to check it out, there's the URL. Simple site, basic information, basic status.
I think it's also available for access from the TCNJ's senior project page.
Yes.
So if you, yeah, want to take a picture.
And this is the light detector that we're using to find or pick up the flash of the lightning. Photo detectors there have a potentiometer here that we can adjust the sensitivity. These are active high, so when they're not picking something up, they're outputting 1, and when they pick something up, they drop to 0. And this over here is going to be the device that mounts these two so that they can be spread out in a circle and get a good 360 dome of the sky.
So we can see all around it and above it, but we're not detecting anything below it, so we don't get like arbitrary flashes from like reflections from car lights or anything of the nature.
So yeah, you could like put this up on a pole, it's nice and high up, like 10, 15 feet. You lose a lot of false positives.
So moving on to the antenna design, we are looking to detect a 300 kilohertz signal from over a mile away. We don't want to have too crazy of a detection radius because if we're going to be putting this in a place like a park or like a sports field, we don't want it to detect, lightning in the town over, because that's not really going to be too much of a detriment to the park itself. So we want it to be able to have a large enough range to be within the sphere that it's working in, but not go too far out so we're not getting things that are unnecessary. And the 300 kilohertz signal produces a 1 kilometer long wave, which is rather large due to the fact that it's such a low frequency. So based off of that, we're going to need a larger antenna to be able to detect this kind of wavelength. And that is why we decided on a loop antenna, because it is the best and most efficient for the wavelength at lower frequencies. And we are using a passive loop antenna, which means there is no signal being presented to the antenna to generate a magnetic field for detection. So it's going to have a much more precise detection ability. So we're not going to be getting a lot of signals outside of the range we want. So here is the antenna itself. We created a frame loop antenna. It was originally designed as a circle using CAD FICO. And then I took that circle and translated it geometrically into a square because it's a lot easier to make a square than it is to make a circle. It has a 121 centimeter diameter and it has 30 loops back. So, and at that frequency, based off of my CAD FICO analysis, it'll have a self-resonance at around 302 kilohertz. So it's pretty accurate in that regard. And then here we have it attached to an LCR impedance calculator. So we got a 2.3 millihenry inductance on it. So we can then use that value to attach a capacitor at the end of it in parallel to basically create a tank circuit to then have a very, very, very precise resonant frequency. So we can really make sure that we're only detecting the frequencies that we want to use, because there's a lot at lower frequencies, there's a lot of noise just in the air, and that could cause a lot of false positives in case there's some arbitrary light that ends up hitting our photodiodes while some noise coming off of a high powered radio signal passes through. So this is just, we can do that just to make sure we're getting very accurate detection and not getting a lot of false positives. And then we had purchased on the next slide here, we have this test antenna. It is an active loop antenna, which means that it has a power source being pumped into it. Like has a signal being used, which allows it to have a much broader detection range. And we purchased this just so we could test the conditioning circuit and the whole system before we fully hook up the homemade designed antenna. And here we have the output from a network analyzer. So we attached it to one of the ports and we checked the S11 parameter of it. So the return loss of the antenna. So how much power is being reflected back into the port that's being sent out of it. And if the curve is under the -10 sign, that means it's good efficiency to work at a level that we want it to. And if you see here at the bottom of the graph, this is our frequency axis. So this is starting at 50 kilohertz and ending at 500 kilohertz. So you can see here at the -10 line, it starts a little bit after 50 kilohertz and it stays under it for the entire range here. So this was just to make sure that this would work at the frequency we needed it to, which would be 300 kilohertz. And it very clearly does. So this will be good for being able to test our circuit before we're finished building the loop antenna that we have to make sure everything's working the right way. so we can isolate problems better. And then that's a picture of it. You can see that it's a much smaller antenna and has a lot less wiring going on, and that's because of its active nature. It's been able to basically generate a magnetic field around it that we want it to have. So it'll be a lot better at detecting frequencies based off of that signal. So that's everything we have so far for our design. Moving through the semester, we're looking to we just finished connecting the coaxial ports to our hand-built antenna. And during this next week, we're looking to connect it to a network analyzer to get its port parameters to see how efficient it is. And then after that, we're looking to connect it to our conditioning circuit and begin seeing if it can pick up any form of signals at all. Does anyone have any questions?
Can you put up this slide with your email, please?
Our emails?
Yeah.
Oh, the website?
And how many weeks in is this currently in your project?
This is halfway through the second semester.
So last semester was mostly all of our like preliminary design and doing things on the computer and simulations. Yeah, this is our first time working on something of this nature. I've never built an antenna before. So a lot of last semester was learning how to use CAD FICO, figuring out how to really tell if what I'm building is working correctly and things of that nature. And now this semester, we've really been implementing the physical design of this system. So we have a working breadboard for our conditioning circuit. And essentially what that's doing is it's taking the input from the RF signal and turning it into a DC output based off the frequency. And we have a set level at the ADC that it's being sent into. So if it's above this value, it's a good signal. And if it's below it, it's not. So inside of there is an LCR bandpass filter centered at 300 kilohertz. So essentially, and it has a really short bandwidth. So if it's really outside of that range, it's going to produce almost nothing. So that's just to make sure that we're really dealing with exactly the frequency we want.
In scope of your project, your intention to take, get this one instance of it and then build a network of these, like neighboring towns over for it to connect back to your website?
Currently, for the end of this semester, we're only going to have one system working just due to budgeting costs. We get around $300 for a whole group, and we're kind of already pushing that.
Yeah, I wasn't thinking this was all.
Yeah, but in the whole scope of things,
In
yeah.
theory, that's why we wanted it to be connected to the internet so that we could have a network of these to pick up lightning in a region.
Triangulation using time of arrival. So we would be able to see when it reaches each antenna itself and then use like a system of equations to find out like a closer approximation of where the lightning is being struck at.
Have you looked into some of the existing networks that this?
Yes.
Data from this?
Yeah, there is one project that is kind of an open source project. I think it's German originally, so it's called I think Blitzertongue. And it what they do is they have basically open source design of systems for lightning detection. They use a lot more like digital processing and more advanced circuit boards than us. So that was kind of used to just kind of get the stages of the conditioning circuit underway and figure out like what the best way to design the antenna was, which is how we ended up on the frame antenna here. And we decided to just stay with a passive loop because it's a bit easier of a design and requires a lot less like understanding of the network. And so that's why it's a bit bigger than most things that come out. So it's really just so it could resonate it has a self resonance at 300 kilohertz.
Also, on the active antenna, you put a longer wire than it came with it? That was bigger than what I've seen on those.
That's actually what it came with.
Okay, because I've seen
Yeah.
those come with different sizes of different lengths of wire. believe it or not.
Yeah, so that's the
That's what they gave you.
that's the
Yeah.
lead coming out of. So right here is the
Yeah, I'm talking
Yeah.
about the loop.
yeah. This is just exactly what it came with.
They put a couple of those, and they had different amounts of loop.
Yeah,
Yeah.
Like whoever made them, just they don't really just grab it, chunk it.
Yeah. I guess it's because it has an extremely large frequency band that it can work
It
at.
doesn't make that much difference.
Yeah, this can actually work up to 30 megahertz.
This is supposedly,
Yeah, and that's based off of like the power being supplied to it. So I guess it's the size of the active loops that it comes with, or like that actual
Are you doing the 12-volt one or the 5-volt one? They make it both ways.
5-volt.
Okay, so I thought the 12-volt ones had regulator problems that didn't fry.
Yeah,
5-volt ones were better,
yeah.
but then you have more of a risk of getting noise from your power
Mhm.
supplies.
Yeah, because our overall system is going to be working with 5 volts. in general, even with our passive loop. So we wanted to keep it as
Yeah,
set to stone of what we're working on.
I found the fiber optic were reliable anyway.
Yeah.
I played with those things a while back.
You did excellent work. I mean, especially on the antenna that you would pass it. And I would love engineering into the antenna because you chose 300 kilohertz, you're away from the broadcast band, where you don't have false positives.
Yeah.
So even if you had to go so far on the antenna, that it's, never mind the red step. You have to be perfectly present. The fact that you're way on 300 kilohertz and you're getting that coverage, you're fine.
That should work, yeah.
Yeah. Yeah, so-
That's the point.
We had to use RG6 coaxial cable for this because it's a lot cheaper than 50 ohm coax. So what we have is after connecting the coax port to it, we actually got 75 ohm to 50 ohm adapters to screw onto the end so we can actually
Get
like,
a bit of loss. Actually,
Yeah.
you could have just, actually, to be honest, you could have just looked it up directly. It wouldn't got, the SWR wouldn't have been that far off.
You
Yeah.
cannot transmit.
No, I know.
Yeah.
Well, it's a core fixed receive too, just not as severe.
yeah, that was more for the network analyzer portion of it so we can get like a more accurate test on it.
Yeah, that makes, hit it with the signal.
Yeah, because we're only using like a 50 ohm load on the other side. So for testing a 75 ohm antenna with it.
75 ohm cable when you expect it's 52, and a lot of times they just ignore the slightly off ratio.
Yeah,
It works just
the
fine
impedance
anyway.
match isn't too big of a deal since we're at such a low frequency. The wavelength
It's
is
even
so
less
big.
so with those
Yeah,
frequencies, right?
exactly.
And even at HF, and people have been known to do it, or even VHF, I've heard people using cable DV coax, it's dirt cheap.
Yeah, it's honestly also not too big of a deal because if it has a little bit more loss, we're not going to be having too much power coming out of the antenna itself.
Not only that, but you're not running a lot of it, I'm assuming. either.
Yeah.
And it's a thick cable, so that's the loss anyway.
Mhm.
Makes sense?
What's the detection range of this?
We want it to be around a mile or more. Nothing too crazy, just because our original like plan for this was to be for a park or for some form of like.
Summer camp or,
So we don't want it to go way far outside of the range of the summer camp because if it's detecting stuff like 10 miles away, well,
like,
That's-
if it was set up here, we don't care if it's picking something up in like Virginia. Like, that makes no difference to us up here.
Things like that. You avoid things like golf courses and open baseball
Yep,
fields and things like that.
exactly.
Because you have a flat ground with people on it,
yeah,
walking lightning rods, so yeah. that's-
exactly.
I'm sorry, we didn't mean to make you right.
Oh, no, you're good.
No,
I
you're
just
good,
want to
good.
make sure everyone else has time too.